Hello, everyone. My name is Zhao. I'm a applied research scientist from NVIDIA. Today, I'll be happy to introduce our work MAISI, Medical AI for Synthetic Imaging. I will first introduce our major contributors, the challenge goals, the model overview, and then the methods, the experiment, and the summary. The MAISI is developed by our brilliant colleagues, Dr. Pengfei Guo, Dr. Dong Yang, me, under the guidance of Dr. Daguang Xu. And during the development of MAISI, we received tremendous help from from other brilliant colleagues and our collaborators from NIH, University of Oxford, and University of Arkansas. So while we are here, while we are discussing this project MAISI, since I first attended the academic conference in medical imaging, I've been hearing complaints about lack of annotated data. So there are very limited data with high quality annotations in medical imaging domain, especially those with tumors. That is because the expert domain knowledge is needed in the annotation and a long tail problem for deep learning models like rare disease. Also, there are privacy and ethical concerns on sharing medical data, so that's why image synthesis methods are desired. So then the deep learning era come. So everyone are using deep networks for the research work. So after about since 2017, I starting to hear complaints about the lack of GPU resource. We know that we want to develop image synthesis method, and the diffusion models are the SOTA image synthesis methods. However, diffusion models require a large amount of GPU resource to train. In this case, if we can have foundation models released, that foundation models can save GPU hours for the researchers. Then we do the literature search for those existing medical image synthesis methods. We found that there is actually a flexibility issue. Those methods work for single data sets or a few data sets, usually work on limited body region, limited organs or tumors. And usually they work for a specific voxel size or volume size, and they cannot generate large 3D volumes like larger than 512 cubics. That's why we're here. We developed the medical AI for synthetic imaging, which we call MAISI, to address these issues. So here are the goals of MAISI. We want to develop a high-quality 3D CT image generation with or without an anatomy annotations. It can be first used for data augmentation. We want to use it to create realistic medical imaging data, helping to augment the data sets where real images are limited due to privacy concern or rarity of certain conditions. With the ability to generate diverse and realistic images, they can improve other machine learning models in the medical imaging. So the second goal is to save annotation effort. MAISI can be used to generate image and label pairs based on user-specified anatomy classes. And we hope that it can generate synthetic medical images be more cost-effective than collecting and annotating real data. Another goal is for ethical use of data. We hope MAISI to provide ethical alternative to using sensitive patient data, and we hope it to produce a wide variety of medical images for educational purpose, helping training and medical students in the diagnostics without needing access to confidential patient records. Last but not least, we hope that after releasing MAISI as a foundation model, we can save users GPU resources. We hope the MAISI has ability to zero transfer or to fine-tune for the own models of the researchers. Here is the overall overview of MAISI model. MAISI can be used to synthesize 3D paired image and mask. There are a few advantages of MAISI. The first one is that MAISI can be used to generate larger volume size range from small volume like 128 cubic to larger volume like 512 by 512 by 768. This is, as far as we know, the first attempt in realistic CT image dimension. Also, MAISI works for various voxel spacing, or what we call voxel size, and it covers the whole body. It can provide paired image and mask outputs and provide up to 127 anatomical classes, including regular organs and tumors. The two major applications of MAISI, one of them, as we mentioned, is data augmentation. We use MAISI to improve segmentation accuracy with synthetic paired image and mask. And the second application is foundation models. MAISI can be used to save training GPU hours for users. So there are three key components of MAISI. So MAISI intrinsically is a latent diffusion model. The first part of it is foundation variational autoencoder. So this VAE is used for latent feature compression. We trained it with both CT and MRI, so it works for both CT and MRI. And it works with flexible volume size and flexible voxel size. The second part is foundation diffusion model. It can generate large CT volumes up to 512 by 512 by 768 size, and it also works with flexible volume size and flexible voxel size. The third part is control net. Control net can adapt to different tasks. So the control net that we released can be used to generate image and mask pairs that can improve the downstream tasks. And it works for controllable organ or tumor size. There's one thing that we want to highlight about MAISI is its expandability. We can see that there are three parts of MAISI. Two of them are foundation models. So if you are a user of MAISI and you want to apply MAISI to a different task than segmentation, the users can reuse the foundation VAE and foundation diffusion model while only retraining your control net. That greatly saves the GPU resource. So here is the inference API of MAISI. So there are three kinds of inputs. So the first input is a must-have input. So for the users, we would like users to specify the volume size you want and the voxel spacing with the unit of millimeter. For example, the user can specify that I want a 512 by 512 and 768 volume size with a resolution of 1 by 1 by 0.8 millimeter. So the second kind of input that the user can provide the body region, whether they want head, they want chest, abdomen, and lower body, just name it. The third one that the users can provide for MAISI is the interested anatomies. So there are up to 127 classes the users can specify. For example, if the user said, okay, I want a hepatic tumor, then the MAISI will output a synthetic image and the paired hepatic tumor mask for this image. So in this case, whatever organs among these 127 or tumors the user specify, MAISI can output paired images and a mask. So here is a example, is a screenshot of the GUI demo interface. So I put the website here. We can see that the user specified abdomen. Let me use the laser point. Yeah, the user specified abdomen and specified anatomy masks. The user is interested, including liver, spleen, left kidney, and right kidney, and specified the XY dimension 256 and the Z dimension as 256, and specified the spacing of millimeter of 1.5 millimeter cubic. So and then the user click run here. So after some time of generating, on the right-hand side, the results show up like this. It includes the image and all the anatomy labels here. Next, we will introduce the training algorithm of MAISI. So as we mentioned, the MAISI have three parts. The first part is a VAE GAN. So we train a VAE GAN to compress the medical images to 3D image features. So all the network in the MAISI are 3D networks. And we use the standard L1 loss, the perceptual LPI plus loss, KL loss, and the vocabulary loss. to ensure that the reconstructed image will have a good quality. The second part is a foundation diffusion model. The foundation diffusion model, one thing that differs MAISI diffusion model with a standard diffusion model is that it takes the body region and voxel spacing as input to generate to generate the 3D image features. Later, the image features can be used to reconstruct the 3D images. The third part is a control net. So for the control net we released, the control net takes a 3D segmentation mask as an input and use this mask to generate the paired 3D image features. Next, I will introduce how we prepared the training data. To train the foundation autoencoder, we trained it with 39K CT data covering the whole body and 18K MRI data covering brain, scalp-stripped brain, chest abdomen. So all trained at the same time to train the same foundation VAE model. And to make it flexible, we randomly zoom the original image to support various voxel size. The second part is foundation diffusion model. We trained the foundation diffusion model with over 10K CT subjects from 24 datasets covering a whole body. The data distribution is shown as below. So the first one is the volume size. So we can see that the distribution. So this is the distribution of the original image. It covers a large range of the image size. And the right hand is the dataset voxel spacing with the unit of millimeter. And we can see it covers a large range of image voxel spacing. The third part is control net. The control net can adapt to different tasks. Here we trained two control nets sharing the same foundation VAE and the same foundation diffusion model. As we mentioned that for a user with different tasks, the user can choose just to train the control net and just reuse the foundation VAE and the foundation diffusion model. Here, the first control net, we call it MAISI CT generation. It takes a mask as input, generate paired images. To train this control net, we use 6K CT image and the auto-segmented mask as training data. So the mask have 127 classes. The second control net is MAISI InPaint. It takes image and the tumor mask as InPaint, and it can be used to InPaint the tumor on the healthy input image. We use only several hundreds of medical segmentation decathlon images and the tumor mask as training data. And here is the inference algorithm that the user just provides some randomly 3D noise, and here is the 3D segmentation mask and body region and the voxel spacing. And it can generate the 3D image features, and we decode the image features to generate the final 3D medical images. We talked a lot about this advantage, about what it can achieve, and what's the algorithm. Here we want to do some performance evaluation. The first part we want to evaluate is the foundation VAE. We claim it to be foundation VAE, so we want to test whether it is true foundation. We want to test whether this VAE can zero transfer to unseen datasets. The datasets we are experimenting including the MSD pancreas tumor, MSD hepatic vessels, and breast 18. The metrics we are evaluating SSRM and PSNR and the LPI-PS loss as a perceptual loss. We are comparing two things. One is to directly apply MAISI VAE. We directly apply the MAISI VAE to unseen out-of-distribution datasets. So during the MAISI VAE training, we have never seen data from these three datasets. So the second we want to compare is the dedicated VAE, which means that we train new in-distribution VAE based on those datasets. So it's an in-distribution VAE. We are comparing out-of-distribution MAISI VAE with in-distribution dedicated VAE. So how it goes? So here are the results. In this table, we compare its results on CT and MRI data. We can see that the MAISI VAE and the dedicated VAE can at least achieve a comparable performance on the datasets, while we do not need to add any training GPU hours for MAISI VAE. So the GPU hour you need to spend is just zero transfer rate. While if you want to train dedicated VAE for each new dataset, you will spend over 600 GPU hours. So that means if you are using our MAISI Foundation VAE, it's very likely that you can save several hundreds of GPU hours. The second part we want to evaluate is the foundation diffusion model. Here is some qualitative results. So the first one is a comparison of MAISI diffusion model with several different kinds of methods. So DDPM is that if we do not use a VAE, we just we just train a diffusion model for image directly without any latent features. So this is the result like this. Because it takes a lot of GPU memory, we have to train it with low resolution. That's why it looks blurry. So the second row is the vanilla latent diffusion model. It's the same the latent diffusion model, but in MAISI, we made some modification to it. So that makes MAISI a better performance. The third one is a GAN method. And so we can see that the GAN did not that work well on those on this comparison experiment. And the right-hand side is we want to test whether this MAISI diffusion model can really generate various volumes and various voxel spacing. And you can see that the first image is a 256 cubic with 1 millimeter voxel size. And second image is a different voxel size as 1.5 millimeter. And the third image is a very large image by 512 cubic with a voxel spacing of 1.5 millimeter. Next, we want to have some numbers. We want to test whether the synthetic images look like real city images using FID. FID is a metric as measuring the distance between feature representations of real and generated images. So we use FID to test whether generated images look like real city images. The first experiment is we are comparing MAISI diffusion model synthetic images to in distribution real city images. So in distribution means that during the training of MAISI, we have already seen these real city images. In this table, the first three rows about real means that it's the FID between real dataset to real dataset. So we know that there are a lot of CT datasets. We want to know that what is FID between different real datasets. That gives us a upper bound that if we train our model to what's the upper limit we can have. So we can see that even between the real images, the FID is like around 3 or 4. While here the last two rows are the FID between synthetic images and real images. We can see that MAISI can achieve FID around 4, 6, 8, which is not as good as real to real. Of course, that's the upper bound, but already pretty close. And next, we want to compare MAISI diffusion model to auto distribution real city images. We claim to be foundation, right? We claim to be foundation. You need to have zero transferability. So here we compare MAISI results with auto distribution real city images. Here we compared with a dataset called AutoPet. We have never seen this dataset during the MAISI training. And here is the result. We compare with several comparison methods, and the MAISI can achieve FID, average FID of 6. And we recall that the real to real FID is around 3 or 4, so it's already pretty close. The third part we want to evaluate is control net. Here we want to test whether control net can improve the performance of segmentation. We claim that image synthesis can be used for data augmentation, right? So here we see whether this data augmentation is really useful or not. We mentioned that we trained 2 control nets. The 2 control nets sharing the same VAE and the same diffusion model. The first one is MAISI CTGen. It generates image mask pairs. The second one is MAISI InPaint. It imprinted tumors on healthy input CT images. And here is the result. We trained segmentation networks on real images only. So here we call it real means that we train a segmentation network only using real data. And real plus thin means that we mix the real and synthetic data for training to show the effect of synthetic data for data augmentation. And here is the table, the figure, that after using comparing with real images, MAISI CTJ and MAISI inpaint can always give you a boost on the segmentation dice. So the y-axis is a dice. And we compare it with a method called diffusion. It's also a really good method. It's a inpainting diffusion model. So we can see that the MAISI CTJ, MAISI inpaint can always give you a boost on your segmentation. We show that it is useful as a data augmentation method. Last, I want to introduce a real application of MAISI. So here we just follow a typical way of writing a research paper. We say that here's our method, here was the experiment. But whether this method can be used in real application, here is an example. We really use it. Yufan, as is the last presentation, is by Yufan. Yufan just introduced the Vista 3D, which is a foundation segmentation model. As he already introduced, it's a really cool method. It can zero transfer to even monkey data. So when we are training Vista 3D, we met an issue that there are a lot of labeled organs. So if you search for public data sets, there are a lot of annotated organs, but there were limited annotated tumor. So annotated tumor data is something that we desire, but we don't have enough of them. So here is how we use MAISI. We use the MAISI CT generation to increase the number of tumor training data for Vista 3D by 100%, which means that if there are 100 real images, we synthesize 100 synthetic images. So that's what we call we increase the number by 100%. So this increases the tumor segmentation performance while not affecting the segmentation performance of other anatomy structures. And here is the table. So it's a table specifically for tumor segmentation. So we can see that Vista have had 2 released already. So one is the last year's RSN release, one is this year's release. We can see that between the 2 releases, Vista 3D, although after some modification, it only improves the tumor segmentation dice by only 0.3%. That's a really small increase. Then we added some synthetic data. We use MAISI to provide some synthetic data for it. And it gives a relatively larger boost of 2.3% for the dice result. So this is a real application of MAISI. To summarize, MAISI is a 3D medical image latent diffusion model. It consists of 3 parts: a foundation VAE, a foundation diffusion model, and a control net that can adapt to different tasks. And here we show 2 applications. One is the data augmentation. It improves segmentation accuracy with synthetic paired image and the mask, as we just showed in the last slide. We already use it for Vista 3D. And we released a control net that can output image mask pairs used for data augmentation in our segmentation foundation model Vista. And the foundation VAE and the diffusion models can be used to save training GPU hours for the users. There are many advantages of it. One of it is large volume size range. It's the first attempt in realistic CT image dimension, and it can work for various voxel spacing. It covers the whole body, support up to 127 anatomical classes, including regular organs and tumors. And if users want to apply to different tasks, users can just reuse the foundation VAE and foundation diffusion model while only retraining the control net. Thank you. So it's time for questions. So this is my email, and this is our paper. We have open source code, we have GUI demo, and we have already released all the model checkpoints. So you can just download the model checkpoint and fine-tune your own model based on our MAISI. Thank you.